Okay guys, here's what we're gonna do here. I'm hoping that we can do this in class, but I don't know if we'll have the opportunity to do it. So if we do, great. If we don't, then at least we have it on video. Okay, so there is a pattern here. Okay, and notice what I'm doing. I'm starting with a horizontal line, y equals c, where c is some constant. And then I add one factor of x, so y equal x, and then a second factor of x, y equal x squared, third factor of x, y equals x cubed, and so on. And we're going to see if you can figure out what the pattern here is when we take the derivative. Okay, so we have our function here, okay, and we're going to figure out our derivative, and then we're going to compare them, okay, and see if you guys can figure out what that pattern is, because there is a pattern, okay? All right, so let's start here with f of x equals c. Okay, so if I use the alternate method, so we say the limit as x approaches a of f of x minus f of a all over x minus a. Now if we look at that, f of x is c, well so is f of a, because it's a horizontal line, so all the y coordinates are c, so we just get c minus c over x minus a, so we're going to get 0 over x minus a, which obviously is 0. So if we take the derivative, okay, at any point, okay, on a horizontal line, we're going to get the slope, which is obviously 0. Okay, so no big deal there. All right, now this guy right here, f of x equals x, that's just y equal x. That's a line, okay, y equal x. Okay, so if I take the slope of any tangent line anywhere, I should just get the slope of that line. I should just get 1. So let's see if it works out. Okay, so we go the limit as x approaches a of f of x minus f of a all over x minus a. Okay, so let's see. That's going to give me the limit as x approaches a. Well, f of x is x, and then f of a would just be a all over x minus a. So clearly that reduces down to 1. Okay, so let's see. So the derivative of y equal x, or f of x equals x, we just get 1. And now both of those make a lot of sense. Okay, figure this is a horizontal line, so no matter where you're at, the slope of any tangent line will be 0. This is the line y equal x. Okay, so no matter where you go, the tangent line will lie right on top of the original function. Okay, and so the slope of the original function is 1, so the slope of any tangent line should be 1 as well. Okay, let's see what happens here. Okay, so I go the limit as x approaches a of f of x minus f of a all over x minus a. Okay, so f of x is just x squared. Okay, so that'd be x squared. F of a would just be a squared. Okay, so we take a look at that guy and you say, okay, well, isn't that just a difference of squares up in the numerator? Okay, so I get the limit as x approaches a. Well, if I factor that, I'm going to get x plus a times x minus a, like that, and that's all over x minus a. So obviously the x minus a's cancel, and I get the limit as x approaches a. It would just be the x plus a. Okay, so if as x approaches a, if I evaluate, I just get a plus a, or 2a. Okay, now we're writing our derivatives in terms of x. Okay, so I could write that as 2x. Okay, so my derivative here is 2x. Okay, all right, let's go down to f of x equals x cubed, and I might need a little bit more room. Okay, so let's see what's going on here. Okay, so let's see, we go the limit as x approaches a of f of x minus f of a all over x minus a. Okay, so I use my function, limit as x approaches a, f of x is x cubed, minus f of a would be a cubed, all over x minus a. Now, we ask ourselves, do we have a factor of x minus a up above? And we certainly do. Okay, so you could either do the long division or go back to that formula I gave you. Okay, this is a difference of cubes. Okay, so I know I'm going to get x minus a times x squared plus x times a, or ax, plus a squared, like that. Okay, so I get the limit as x approaches a, and notice the x minus a's cancel off, so I just get x squared plus ax plus a squared. And then I evaluate when x becomes a, so I'm going to get a squared plus, notice this will be a times a, okay, or a squared plus the a squared. And notice that'll give me 3a squared. Now, we're writing our derivatives in terms of x, so 3a squared, I can just write it as 3x squared. Okay, 3x squared. Okay, so far so good. Let's move that guy up. All right, now we got to do f of x equals x to the fourth. Okay. So I have the limit as x approaches a of f of x minus f of a all over x minus a. Okay, so I substitute in f of x is just x to the fourth. F of a would be a to the fourth all over x minus a. Now we ask ourselves, is there a factor of x minus a up in the numerator? And yes, there is. Okay, I know there is. Okay, so I have this factor of x minus a up above, factor of x minus a down below. So we got to figure out what are we left with here. Okay, so you got to do the long division. Okay, so let's do that long division. Let's see what happens. Okay, I have x minus a. Okay, let's see. I start off, I have the x to the fourth. Now I need an x cubed. I don't have one, so it'd be plus 0x cubed. I need an x squared, which I don't have it, so it'd be plus 0x squared. I need an x to the first. I don't have it, so it'd be plus 0x to the first, and then minus that a to the fourth. And remember, a to the fourth is just a constant, okay? And so I'm going to do this long division. So x to the fourth divided by x is x cubed. X cubed multiplied through, and so I get x to the fourth minus ax cubed, and then I subtract. So these go away, and then notice it's minus a negative, so that would be plus ax cubed. Bring down the 0x squared. Okay, so ax cubed divided by x will be ax squared. Multiply through, so that'll give me ax cubed minus a squared x squared. And then we do our subtraction. Of course, these cancel off, and you have minus a negative. So I've got a squared x squared. Bring down the 0x. Okay, ax squared divided by x will give me, I'm sorry, a squared x squared divided by x will give me a squared x. So I get a squared x. Multiply through, I'm going to get a squared x squared minus a cubed x. And then we subtract. Okay, let me move this guy up. Okay, so these cancel off, we know that. And I have minus a negative, so I have a cubed x. Okay, and then bring down the minus a to the fourth. Okay, so a cubed x divided by x is a cubed. Multiplied through, so I'm going to get a cubed x minus a to the fourth, and obviously when you subtract, you get nothing. Okay, so here we go right here. Okay, so let's see. When I factor out an x minus a, I'm going to be left with x cubed plus ax squared plus a squared x plus a cubed. Okay, so this guy cancels, that guy cancels. And let's see what we're left with. So we are left with the limit as x approaches a of x cubed plus ax squared plus a squared x plus a cubed. Then obviously you would just have 1 down here, so it just goes away. So you say, well, what happens? As x approaches a, this becomes a cubed. Okay, this will become a times a squared. This will become a squared times a, and obviously it doesn't affect the a cubed. So you say we have an a cubed here, we have an a cubed there, we have an a cubed there, and we have this a cubed right there. And so when you add them, notice you're going to get 4a cubed. And since we are doing derivatives in terms of x, I would write that as 4x cubed. Okay, so this guy is 4x cubed. Okay, now we could do this one, and obviously this last guy is going to be very similar to this. Okay, if we have time in class, we will go through it. I will tell you what you're going to get. You're going to get 5x to the 4th. Okay, so we look here. Is there a pattern? Is there a pattern? Okay, are we doing something and doing the same thing all the way through? Okay. Well, you figure this c, wouldn't that guy be the same as c times x to the 0th power? Because x to the 0th power is just 1. And so what if I take this exponent and I put it out front? I'm sorry. Yeah, cx to the 0th power. Yeah. And what if I do this? I'd move this exponent out front and then subtract 1. So I would get 0 times cx to the negative 1st, which would just be 0 right there. Okay. And let's see this guy. Okay, this is x to the 1st. What if I do the same thing? Take this exponent, put it out front, and then subtract 1. So I would get 1 times x to the 1 minus 1 is 0th. So that would just be 1 times 1, which is 1 right here. Okay, I'm doing the same pattern, notice. And what if I take this guy and I say, okay, x squared. What if I do the same thing? Take this exponent, put it out front, and then subtract 1. So I would get 2x, 2 minus 1 is 1, so that's just 2x. That's exactly what we get. And notice I'm doing the same thing. Okay, let's take this x cubed, and let's suppose we use the same pattern. Let's take the 3, put it out front, and then subtract 1. So I'm going to get 3x to the 3 minus 1 is 2. Notice that's what I get, 3x squared. Okay, let's do the same thing here. We take that x to the 4th. I take that 4, move it out front, and then subtract 1. So I get 4x, 4 minus 1 is 3. I get the same thing. Okay, let's do the same thing here. Let's take this x to the 5th. Let's move the exponent out front and then subtract 1. Notice I get 5x, 5 minus 1 is 4. I get the same thing. You've got a pattern going on here which establishes what we call the power rule, okay? Very important. If I were you guys, I would certainly run this off from the notes that I have in Google Classroom. So if we have a horizontal line, f of x equals c, so we have a constant function, c is a constant, then the derivative always gives me 0. Okay, so the derivative f prime of x would just be the derivative of f with respect to x, which is d dx of c. So if we're taking the derivative of a constant, we just get 0, always. Okay, and that makes sense because you figure the derivative would be the slope of a tangent line. And so we would have the slope of a tangent line to a horizontal line. So all the tangent lines have to be horizontal as well, so the slope's always 0. So that makes sense. Okay, so if we are taking the derivative, okay, of something where it's x to the nth, so let's suppose if we take f of x equals x to the nth, okay, where n is any positive integer. Okay, so we're taking the derivative of x to the nth, and what we do is we take the exponent, we move that out front as a coefficient, and then we subtract 1 from the exponent, and that gives us our derivative. And so what's nice is we don't have to go and do Fermat's method anymore because we've got a shortcut, which obviously we all like shortcuts, okay? So let's apply this rule to some very basic polynomials, okay? Taking derivatives of polynomials, okay? Very basic stuff, okay? So this stuff isn't hard at all. I mean, once you get the hang of it, this stuff is really, really easy, okay? One of the great little shortcuts in mathematics. Okay, so let's see. So this first one, okay, we're starting with f of x equals x to the 9th. Okay, so I want to do the derivative, f prime of x. Now remember, that's the same. I don't have to use the prime notation. I could say, you know, dy, dx, whatever, okay? So when I apply that, I take the 9, I put it out front, times x to the, I subtract 1 from the exponent. So we just get 9x to the 8th. And there's your derivative, okay? It's that simple. Okay, so this guy right here, okay, I have f of x equals x to the 12th. And so if I take the derivative, f prime of x, and remember I could say dy dx if I wanted to. I could even do this. I could say, okay, what's dx, okay? So we take the 12, we move it out front, and then we subtract 1 from 12. So we get 12x to the 11th. That's it. Okay, it's all you got to do. Okay, let's go down to the third one. Okay, f of x equals 3x to the 6th. Now remember, a derivative is a limit, okay? So we know that this guy acts as a constant multiplier. So we could just put that guy out front and take the derivative of x to the 6th and then multiply him at the end. So we have that 3. Okay, so I take the exponent, move it out front, and then I subtract 1 from the exponent I started with. So notice you're going to get 18x to the 5th. Okay, so far so good. Okay, number 4. Okay, f of x equals negative 7x cubed. Okay, so if I do my f prime of x, okay, and notice I used this guy, used that guy. Notice you could also say, okay, what's d dx? Doesn't make any difference. So again, that negative 7 is a constant multiplier. It's a GCF. So just put that out front and then take the derivative of x cubed. So the 3 goes out front, and then we subtract 1 from the given exponent. So I'm going to get negative 21x to the 2nd power. Okay, so far so good. What do I got left? Okay, let's see. Well, remember your rules for limits. If we have a limit of a sum or a difference, I can take the limits of each guy one at a time, okay? So I can do the same thing with the derivative. So if f of x equals 16x squared minus 3x, then f prime of x, I could just take the derivative of each term, okay? So I'd go d dx of the first term, 16x squared minus d dx of the second term, 3x. Okay, and just do my derivatives like that. Let's move this up so I have a little bit more room here. Okay, so look there. Notice 16 is a constant multiplier, so just leave that guy out front and take the derivative of x squared. So move the 2 out front and then subtract 1 from 2 minus, again, notice that's 3x to the first, so put that 3 out front and just take the derivative of the x. Okay, so that's x to the first, so it would be 1x, and then we'd subtract 1. Okay, so let's see, this is going to give me 32x to the first, which is just 32x. And then notice this will be 3 times 1, which is 3. That'll be x to the 0th, which is 1. So I just get minus 3. Okay. All right, so let's see. Let's move this guy up and let's get this last one. Okay, I've got f of x equals, that's x cubed plus 6x squared minus x minus 9. And then I just take them one at a time. Okay, so my f prime of x, it'll be the derivative of this guy. Okay, so obviously you have a 1 here as a coefficient, so it's 1 times, so that 1 doesn't really do anything. So bring the 3 out front, x to the 3 minus 1 power. Plus, you got a 6 out front, and then take the derivative of x squared. So bring the 2 out front, x to the 2 minus 1. Minus, notice you have 1x to the first, so bring that 1 out front, and then it would be 1 minus 1. Okay, and then minus, anytime you take the derivative of constant, you get 0. Okay, so let's see, what do we get? We get 3x squared plus 12x to the first, okay, minus this would be 1 times x to the 0th. X to the 0th is 1, so you get 1 times 1 or just 1. And we're done. And notice how easy it is to do this stuff. And now you don't have to use limits. You don't have to go back to Fermat's method because we've got a great shortcut.